All right, let's talk about a moment that really feels like it's straight out of science fiction, a moment that will go down in the history books of computing. We're diving into a breakthrough where a totally new kind of machine did something our absolute best supercomputers simply can't.
Okay, let's just jump right to the chase, because this is the claim that made everyone's jaw drop. Back in 2019, Google's team said their quantum processor, named Sycamore, nailed a specific task in just 200 seconds. Now get this, they calculated that the world's #1 supercomputer would need about 10,000 years to do the same thing. You heard that right, 10,000 years.
So that leaves us with one massive question, and it's the one we're going to unpack here. How? How in the world did this new machine pull off a calculation that would take a classical computer longer than all of recorded human history to solve?
To really get what happened, we need to understand the obstacle they were up against. You see, there's a kind of fundamental limit, a wall that our regular computers run into, even the massive, room-sized ones. Some problems are just too hard for them.
The legendary physicist Richard Feynman saw this coming way back in the 80s. He pointed out that our universe, at the tiniest level, plays by the super weird rules of quantum mechanics, and trying to simulate that reality with our normal computers, with their simple zeros and ones, is a nightmare. The complexity just explodes. So Feynman had this brilliant, game-changing idea. What if you built a computer that worked on those same quantum rules?
And that one idea kicked off a decades-long quest. Later, another physicist, John Preskill, gave the finish line a name, Quantum Supremacy. That was the goal, the exact moment a quantum computer could do something a classical one couldn't. And that's the race that led right up to this 2019 experiment.
So what's the machine that finally smashed through that wall? Well, it's time to meet the star of the show. And this isn't just clever software, folks. This is a very real, incredibly complex piece of hardware called the Sycamore processor.
So how does this thing work? Well, your phone or laptop uses bits, right? They're like light switches, either on or off, a 1 or a 0. Simple. Sycamore uses qubits. A qubit is more like a dimmer switch. It can be a 0, a 1, or it can be a mix of both at the same exact time. This bizarre quantum trick, called superposition, blows the doors wide open for computing power.
And here it is. That's the actual chip. It's a grid of 54 qubits, though one had the day off, so they ran the experiment with 53. Each of those little crosses you see is a qubit, all wired up to its neighbors. And to get this thing to work, they have to chill it to temperatures colder than deep space. I mean, we are talking about an incredibly delicate piece of technology.
So, why is 53 such a magic number? Because the number of possible states it can explore at once is 2 to the power of 53. That's a number with 16 digits, over 9 quadrillion. It's a number so outrageously large that no classical computer on Earth has enough memory to even write it down, let alone calculate with it.
Now, this is a really crucial point. Sycamore wasn't trying to predict the stock market or anything useful like that. It was given a very specific, custom-built problem. Think of it as a racetrack designed specifically for a Formula One car. The whole point of the task was just to prove that it could do something, anything, that a regular computer couldn't. The researchers themselves used a fantastic analogy for what they were doing. Imagine you shine a laser pointer through a piece of frosted glass. You don't get one clean dot, right? You get this messy, speckled pattern of light. That's basically what the output of the quantum computer looked like. Not one clean answer, but a whole pattern of probabilities, where some outcomes are very likely and others are almost impossible.
So the whole experiment really boiled down to 3 steps. First, they linked all 53 qubits together in a complex web using a process called entanglement. Second, they basically just hit go and let all that quantum weirdness create that messy, speckled pattern. And third, they measured the result 1,000,000 times. The whole challenge was this. Could a classical computer predict which parts of that speckled pattern would be the brightest?
And all of that led to the big reveal, the moment of truth. After running the whole thing, the team had to prove, without a shadow of a doubt, that they had actually done it, that they'd crossed the line into quantum supremacy.
And this one chart from their paper is the smoking gun. It's beautiful. Along the bottom, you have how hard the problem is. As they make the task more complex, moving from left to right, look at that red line. That's the time it would take a supercomputer to do the math. It just goes vertical. It skyrockets from hours to weeks to years, and then bam, to 10,000 years. The quantum processor was officially playing in a different league.
And for that final, hardest task, the one that would take a decade, a millennia for the supercomputer, Sycamore gathered all the data it needed in 200 seconds. Let that sink in for a second. 10,000 years versus about 3.5 minutes.
And that is what quantum supremacy is all about. It's not about being smarter at everything. It's about finding that one specific problem where a quantum machine isn't just faster, but so overwhelmingly, ridiculously faster that our classical computers are, for all practical purposes, left completely in the dust.
So why does this one weird, specialized task matter so much? Because it was the first time this had ever been done. It was the proof. It showed that this incredible quantum speedup isn't just a cool idea in a textbook. It's something you can actually build and run in a lab. It's real.
This achievement was called a Sputnik moment for computing, and for good reason. It was a clear signal that a new era had begun, and it naturally leads to the next question. So, now what?
Well, welcome to what John Preskill calls the NISQ era. That stands for Noisy Intermediate Scale Quantum. Intermediate scale means we're still talking about machines with dozens of qubits, not millions. And noisy is the key part. It means these early machines are delicate. They're easily disturbed and they make errors. They're not the perfect, flawless quantum computers of science fiction. Not yet, anyway.
But even in this noisy, early stage, the potential is just mind-boggling. The paper itself lists some of the possibilities, things like generating truly unhackable random numbers, solving massively complex optimization problems, and maybe even revolutionizing fields like machine learning, materials science, and discovering new medicines by simulating molecules in a way we've only dreamed of.
But let's also be realistic here. The really world-changing stuff, like using quantum computers to break today's powerful encryption, is still a long, long way off. To get there, we'll need huge technical leaps in building bigger and more stable machines that can correct their own errors. Think of this experiment as the Wright brothers' first flight at Kitty Hawk. We've proven we can fly, but we're not building jumbo jets just yet.
But what a first flight it was. And the researchers ended their paper with this incredibly powerful and optimistic idea that I think is just perfect. We now have a new kind of computational power in our hands. The hardware exists. The real question is, what are we going to do with it? What brilliant new algorithm, what creative idea is just waiting for this machine to make it possible?